Hi all, I am Josel and my guide is Miss Anuja George. Today I would like to discuss about my seminar topic Optical Satellite Communication. These are the main contents I would like to discuss: the introduction, history, how satellite communication work, link design of satellite, basic principles of OSC, the block diagram, components of OSC, RF versus optical comparison, types of OSC, challenges and solutions, recent technological advances, real-world examples, future prospect, advantages and disadvantages, application, conclusion, references. As we know that successful landing of Chandrayaan 3 is a major milestone for India's space program. Also, the successful launch of ITL-1 is a further testament to India's growing capabilities and space exploration. In this seminar, we are going to explore the potential of optical satellite communication in revolutionizing the data transfer of remote sensing, high-speed internet access, and inter-satellite links, etc. in the modern world. The role of satellite communication is very relevant in the modern world as also in the future. It has a lot of application. First of all, I am going to discuss about what is optical satellite communication. Optical satellite communication, which uses light waves, typically laser beams, to transmit data between satellite and ground stations. Also, it offers higher data rate up to 100 terabits per second compared to the traditional radio frequency communication, enabling faster data transfer. Also, the communication satellite equipped with optical terminals can establish high-speed links with other satellite, aircraft, or ground stations. Optical communication systems are less susceptible to interference and conjunction, leading to enhanced security and reliability. On to the next slide, let me explain the history of optical satellite communication. In 1960, first optical communication experiment conducted between two ground stations. After that, in 1970, first laser communication experiment conducted between satellites. In 1995, first successful laser communication link from space between JAXA's ETS-VIGO satellite and a ground station in the Tokyo. After that, in 2001, first laser intersatellite link achieved in space by the European Space Agency satellite Artemis. After that, in 2010, first commercial optical ISLs developed by the Telesat and Eutelsat. In 2020, optical satellite communication market estimated to be worth 1.5 billion. After that, in 2022, the first optical satellite communication constellation is launched by the OneWeb. Finally, in 2023, development of new laser technologies and the deployment of constellation of OSI satellite. On to the next slide, let me explain how satellite communication work. There are three stages which are involved which explain the working of satellite communication. These are uplink, transponders and downlink. Let me explain them in detail. From the figure we can see the uplink connection and the two ground stations and also the downlink to the from the satellite. The communication satellite are similar to the space mirrors that help us bounce signals such as radio, internet data and television from one side of Earth to another. These three stages which are involved which explain this working of satellite communication. First one is the uplink. In the initial stage of satellite communication, signals such as television broadcast from one side of Earth transmitted upward from a ground station on Earth toward the communication satellite. This step is known as the uplink. Then the transponders are crucial stage involves the utilization of the transponders which serve as a key component within the satellite. These transponders functions such as radio receivers, amplifiers, and transmitters. They play a pivotal role in enhancing the incoming signal strength and altering its frequency. By doing so, transponders ensure that outgoing signal maintain their integrity. Next one is downlink. The final stage of satellite communication involves the downlink, where the data is transmitted from the satellite back to the Earth. This transmitted data is received by the receiver on Earth's surface. On to the next slide, let me explain the link design of the satellite. This mainly include wavelength and polarization, link budget for an asymmetric link, pointing, acquisition, and tracking. In wavelength and polarization, optical satellite communication uses light waves for data transmission. Selecting at the appropriate wavelength is crucial as it affects factors like signal propagation and interference. The choice of wavelength depends on the atmospheric condition and available technology. The link budget for an asymmetric link means link budget are indispensable tools for evaluating the overall system performance. Asymmetric links where data rate differ between the uplink and downlink necessary materialize budgeting. Balancing the power budget for both directions is vital to ensure reliable communication. This involves considering factors like transmitter power, receiver sensitivity, atmosphere losses, and link margins. Next one is pointing. Precise pointing and acquisition mechanisms are pivoted to establish and maintain link between the satellite and ground stations. Pointing involves orienting the satellite optical system towards the ground station, while acquisition is the process of initially capturing the signal from the ground. This process demands sophisticated tracking systems and algorithms ensuring continuous alignment even the satellite is in the motion. Next one is tracking. Satellite tracking is an ongoing task to compensate for the relative movement between the satellite and Earth. It involves real-time adjustment to keep the optical beam centered on the ground station's receiver. On to the next slide, let me explain the basic principles of optical satellite communication. The first one is the information signal is modulated onto the light beam. Then the light beam is transmitted through the atmosphere to the receiving station. At the receiving station, the light beam is demodulated to recover the information signal. The atmosphere can attenuate light beams, which can reduce the data rate and increase the error rate. Also, the pointing accuracy of the satellite and ground stations must be very high in order to ensure that light beams are properly aligned. On to the next slide, let me explain the block diagram of block diagram of optical satellite communication. The key components of optical satellite communication are data source and encoder, the modulator and laser, telemetry and atmosphere, detector and demodulator, then decoder and data. Let me explain them in detail. In data source and encoder, which means the process begins with a data source, which could be any device or system generating information. The data is processed through an encoder, which converts digital information into suitable form of optical transmission using modulation techniques to prepare it to transmission via lasers. And the modulator and result. The modulator plays a crucial role in the optical satellite communication. It takes the encoder data and modulator onto the laser beam. The modulation ensures that data is encoded onto the optical carrier wave, which is a key aspect of optical satellite optical communication. And the telemetry and atmosphere, it is used to monitor and control various aspects of satellite and the communication link. This information is transmitted alongside the data. However, the atmosphere can introduce challenges in optical communication due to factors like atmosphere absorption and scattering, which can affect the signal quality. Next one is detector and demodulator. On the receiving end, there is a detector responsible for capturing the optical signal. The detector converts the optical signal back into the electrical signal. Simultaneously, a demodulator reverses the modulation process, extracting the encoded data from the received output optical signal. Next one is decoder and data. The extracted data in encoded form, it is then passed through a decoder which reverses the encoding process performed at the source. This step ensures that original data is reconstructed accurately. The resulting data is made available for intended use, whether it's for communication, data storage, or other applications. On to the next slide, let me explain the comparison between traditional radio frequency versus optical satellite communication. The traditional radio frequency uses radio waves to transmit data. It has a frequency range of 3 kHz to 300 GHz. In optical satellite communication, we use slide wave to transmit data. It has a frequency range of 300 GHz to 100 THz. Also, radio frequency can achieve data rate up to 100 gigabits per second. Can have a range of up to 100 km. It requires line of sight between transmitter and receiver. It is more susceptible to interference, less expensive, more power efficient. And the optical satellite communication has a range of up to 1 kilometer, does not require line of sight, also more secure, more expensive, less power efficient. On to the next slide, let me explain the types of optical satellite communication. There are mainly two types of optical satellite communication. It is based on the direction of the optical link. From the figure we can see that inter-satellite optical communication. This is the first type. This type of communication is used to transmit data between satellite. It is typically used for applications such as space exploration, Earth observation, and military communications. Intersatellite optical communication systems typically uses lasers to transmit data between the satellites. The next one is satellite to ground optical communication. This type of communication is used to transmit data between the satellite and ground stations. It is used for applications such as high-speed internet access, video conferencing, and telemedicine. From the figure we can see that the satellite to the ground optical communication. The lasers are typically used for long distance links, while FSO links are typically used for shorter distance links. On to the next slide, let me explain the challenges of the optical satellite communications. These are the main challenges of affecting the optical satellite communication. The first one is known as atmospheric attenuation. The atmosphere can attenuate light beams, which can reduce the data rate and increase the error rate. Also, the pointing accuracy of the satellite and ground stations must be very high in order to ensure that light beams are properly aligned. OSS systems are more complex and expensive to implement than traditional satellite communication systems. OSS systems can be susceptible to interference from other light sources such as sun, moon, and other sunlight. OSS systems can be vulnerable to hacking and other security threats. This is because the light beams can easily intercepted and decoded. Apart from the challenges, there are solutions for optical satellite communication uh, with the advancement in technology. The first one is known as free space optical links. FSO links use lasers to transmit data through the atmosphere. This can reduce the effect of atmospheric attenuation. Next one is adaptive optics. Adaptive optics systems use mirrors to compensate for atmospheric turbulence, which can improve the pointing accuracy of the OSC links. Next one is commercial off-the-shelf components. The use of COTS components can reduce the cost of OSS systems. Also, security protocols can be used to protect OSS systems from hacking and other security threats. On to the next slide, let me explain the recent technological advances. The new types of lasers and detectors. These are more resistant to atmospheric attenuation, which can improve the data rate and reliability of the OSC links. Next one is new tracking systems. This can improve the pointing accuracy of the satellite and ground stations, which can improve the performance of OSC links. Also, the new modulation techniques. This can improve the robustness of the signal against interference, which can improve the reliability of the OSC links. For example, the use of forward error correction codes can help to improve the error correction capabilities of the OSC links. And the new coding techniques, this can improve the error correction capabilities of OSC links, which can improve the reliability of the OSC links. Next one is new optical components. These are smaller, lighter, and more efficient, which can make OSS systems more affordable and easier to deploy. This can make, for example, the use of micro electromechanical systems. MEMS technology can help to make optical components smaller and lighter. These are the some of the recent technological advances in OSC. On to the next slide, let me explain the real-world examples for optical satellite communication. The first one is NASA's Laser Communication Relay Demonstration (LCRD). It is a project to develop and demonstrate a laser communication system for use in space. The LCRD was launched in 2021 and is currently orbit around Earth. In the first figure, we can see the NASA's laser communication relay demonstration. The figure 9, it is capable of transmitting data at speed of up to 1.2 gigabits per second, which is much faster than traditional satellite communication systems. Next one is the European Data Relay Systems (EDRS). From the figure 10, we can see the European Data Relay Systems. It is a constellation of satellites operated by the European Space Agency. The EDRS satellite use laser communication to relay data between other satellites in orbit such as Earth observation satellite and weather satellite. Also, this allows for faster and more efficient data transfer. The next one is the Copernicus Sentinel satellite. These are fleet of Earth observation satellite operated by the European Union. The Sentinel-6 Michael Friedrich satellite is equipped with laser communication terminal that allows it to transmit data at speed of up to 100 megabits per second. From the figure 11, we can see the Copernicus Sentinel satellite. This data is used to monitor the Earth's climate and environment. The data from Sentinel satellite is used to monitor the Earth climate and environment. It is used to track changes in the sea level, ice cover and vegetations. Also, it is used to monitor natural disasters such as floods and earthquake. The laser communication terminal on Sentinel-6 satellite is a major improvement over previous satellite communication systems. It allows faster and more efficient data transfer. Next one is the Starlink constellation. The Starlink constellation are equipped with laser communication terminals that will use to beam data between each other as well as to the ground. It is a network of low Earth orbit satellite being built by the SpaceX. This will allow for high-speed internet access in remote areas. From the figure 12, we can see the Starlink constellation. The Starlink constellation is still under construction, but it is expected to have over 2,000 satellites in orbit by the end of 2022. This will make it the largest satellite constellation in the world. The laser communication terminals on Starlink satellite are a key part of the constellation's design. They will allow the satellite to communicate with each other when they are not in the direct line of sight. This will improve the reliability and performance of the constellation. These are just a few of the real-world examples of optical satellite communications. As the technology continues to develop, we can expect to see even more applications of optical satellite communication in the future. The next slide, let me explain the future prospect of optical satellite communication. First one is increased demand for data. The world is generating more and more data every day. Also, the growing need of secure communication. There is a growing need for secure communication, especially in the government and military application. Also, the development of new technologies such as quantum cryptography is making optical satellite communication even more secure and reliable. Also, the cost reduction. The cost of optical satellite communication systems is coming down, making them more affordable for a wider range of applications. We can we can We know that due to the increasing demand for data, the increased use of internet, social media and other data intensive application, optical satellite communication help to meet this demand by providing high bandwidth long distance data transmission. Also it can provide a secure and reliable way to transmit sensitive data. Also, the quantum cryptography uses the laws of quantum mechanism to create unbreakable encryption keys. This makes it impossible for eavesdroppers to intercept and read encrypted messages. Also, the cost reduction. As the cost of optical satellite communication systems continues to go down, they will become more affordable for a wider range of applications. On to the next slide, let me explain the advantages and disadvantages. The advantages mainly high data rate, low latency, better security, wider bandwidth. less interference, and more energy efficient. And the disadvantages are need for accurate pointing and tracking, need for high power lasers, and need for clear line of sight, atmosphere turbulence, interference from sunlight, and the cost. The main applications are uh, these are the telecommunication, high-speed data transmission, Earth observation, space exploration, industrial links, disaster management, telemedicine, and military and defense. On to the next slide, let me explain the market value. The optical satellite communication market is valued at USD 282 million in 2023 and it is projected to reach USD 1134 million by 2028 at a CGR of 32.1% from 2023 to 28. Based on the type, the satellite to satellite communication segment is estimated to lead the optical satellite communication market from 2023 to 28. Also based on the application, the government and defense segment dominate the market and it is projected to witness the largest share in 2023. Based on the laser type, gallium arsenide based lasers seem to dominate this segment and are estimated to account for the largest share of optical satellite communication market from 2023 to 2028. On to the next slide, let me conclude. In conclusion, optical satellite communication represents a remarkable evolution in space-based data transmission technologies, and OSC offers several advantages over traditional radio frequency satellite communication that we already seen. Despite these challenges, OSC is promising technology with the potential to revolutionize satellite communication. As the technology continues to mature, OSC is expected to play an increasingly important role in the future of satellite communication. These are the references. Finally, thank you all.